Hello, this is going to be 2P04 test number 3 recap video, starting with the test from 2016. A space station space module of space mass m is being held by two large space springs, each with constant k on opposite sides of the module, as shown here. They hold the space module in place by having their other ends attached to sides of a much larger space station, as shown. Maybe I should have called those space sides. Sure. Okay, the space module also has an electromagnetic space damper system that prevents its space motion. According to FD is negative BV. If M is 1,000 kilograms, K is 2,000 newtons per meter, and B is 500 newton seconds per meter, first draw the free body diagram. Then we're going to write the net force on the module using x as the dependent variable for the displacement from equilibrium along the line of the springs. Assume a 1D problem. And then determine the natural resonant frequency and quality factor. And if the module is initially at the equilibrium position when it's hit by a photon torpedo, giving it a velocity of plus 50 meters per second, determine how long it takes for the module to settle to within 5 meters of its equilibrium position. Okay, so first thing we're going to do is draw this free body diagram. To do that, we're going to open up paint.net here and grab a rectangle. If you hold shift, you can make it a square. We've got the color palette there, change it back to black for the start. And let's just start off with this thing. That's going to be the space module. So we'll then go over to drawing some coordinates of this. We're going to hold shift to make it snap to a vertical line there. Now we'll get rid of that arrowhead at the end, and we'll label the position of maybe the center of the block sort of displaced from this equilibrium position. So this one is going to be an arrow, and I will change the color of that one to maybe this purple thing, and then put a label on it. So we'll call that X. Then what else can we do? We're going to go and draw the forces on this thing. So now, what will we need? Well, we have a force from each of the springs on this thing. So what's a good force color? How about red? So we've got a force going to the left from that first spring. Depending on how it's moving, we might have a damping force there, and we've got a force from the spring on the other side. So let's call this KX, and then we'll call this BV, assuming that the motion is going to the right at the moment. Okay, so that's pretty much it. That's our free body diagram for this mass spring space damper system. You notice that we drew KX going to the left. That's assuming that the X is in the positive direction. BV, though, really it will depend on what direction the velocity is. So how to demo that? Maybe we could go back and say, let's assume that it's currently moving to the right by adding in a little bit of a velocity on this thing. So we'll call that V. And yeah, okay, so now in this situation, we've got BV pointing in the other direction. So this is a velocity, that's not a force. This is a position, that's not a force, and the forces are in red. Cool. Beautiful free body diagram. 10 out of 10. Great job, team. Okay, so there's our free body diagram. And now we can move on to writing the net force. Okay, so net force on the module. F net is mx double dot, which is equal to negative 2kx minus bx dot. Okay, so yeah, that's pretty much it. So the net force is mass times acceleration, and we've got two springs going opposite to the current displacement and a damping associated with the velocity. Next part is figure out the natural resonant frequency and the quality factor of the module. So this is a classic mass spring system. Even though there's two springs, you see the effect that the second spring has on the system is exactly the same as having one spring with a quality factor, rather with a spring constant of 2K. So if we go back to the lecture notes here, let's get this in a position that you guys can see. Right, okay. So there's this handy section here called Resonant Summary that collects all the stuff we were talking about in all the resonance right up here. Check out the other videos if you haven't seen those on for an intro to how resonance works and mass spring systems work in the first place. The natural resonant frequency is omega naught is root K over M. There's an adjustment to this for damping, but normally it's not a big difference, especially if we are in a resonating system. So we're sort of an underdamped case. So we're just going to use natural resonant frequency root K over M for a regular mass spring system. For this one, it's like we have double the spring constant. So we'll say omega naught is root 2K over M. Great. And the quality factor also brought up here for the regular linear mass spring damper system. This must be the quality factor is not always equal to a half. That must have been something that we were. Oh, this is the continuation of that. Q is a half corresponds to critical damping. Right. All right. So Q is 1 over 2 zeta, which is M omega naught over B, or root MK over B for this system. So we'll say Q is root MK over B. But since we have two springs, it'll be root M2K over B. Cool. So you could substitute in for the numbers that we have there and calculate what that is. If the module is initially at the equilibrium position, when it's hit by a photon torpedo, giving it a velocity of x dot is plus 50 meters per second, determine how long it takes for the module to settle to within 5 meters of its equilibrium position. All right, so for this one, we're going to actually solve the differential equation. And to do that, we'll use Maple here. So we'll put in the parameters that we've got in the program here. So M is 1000, K is 2000, B is 500, and then the differential equation system would be M times the second derivative of x with respect to time is equal to -2 times k times x at t minus b times derivative of x with respect to time. So b times the velocity, and that matches with the equation that we wrote right there. The initial conditions are given in this part D of the problem. And they tell you initially it is at the equilibrium position. X at 0 is 0. When it's hit by a photon torpedo, giving it an initial velocity of plus 50. dx at 0 is equal to 50. So there is our differential equation system. And we can solve that for what the x at t is going to be. We can put that into the decimal version of it, and we can plot it. Oh, right, it's not actually assigned. Cool. So what do they say? figure out how long it takes for the module to settle to within 5 meters of its equilibrium position. From the plot that we've got, it looks like it is going to, so it goes up to plus almost 21 or so, and then back down to negative 14, and then up to almost 10, back down to 6, and then does this get bigger than 5? It doesn't quite look like it. So a couple of ways we could do that. We could plot another function. And that puts a horizontal line of 5 on there. So what I did there was I also added another function in this list. We could add -5 to make that clear, just to see where we are going to be ending up between those points. So it looks like the last time that it is more than 5 away from the equilibrium position is this point right there. So we're going to be looking for where the solution is -5 in this range in particular. So let's zoom in on the plot. Maybe we're going to plot from t is 5 to 6. Okay, and now it looks like it's past 5.5, should be around 5.8, but let's use fsolve to zoom in on that. X at t is -5, t equals 5.5 to 6. And we get 5.82 as the last time that it is that distance away from equilibrium. So how can we summarize this this line of thinking on paper here for if you were going to prepare this in a test situation? Why don't we start off by plotting t equals 0 to 10, and we'll give this whole code. Then we'll say that we'll sort of say what we did. Using dsolve, we can find the solution to this DE and then plot it. Okay, so there's the solution. How about this? The solution, and there is the plot. Oh, you know what we could do? We could improve this plot by putting axes labels on this. That'll make the TAs happy. So to do that, we're going to go into the plot syntax here and say labels equals time and position. See if that works. Yeah, so we could go time and then put it in seconds, and position in maybe meters. Great. So yeah, then what we want to do is say that we've got this there. We can replace that with this plot and say, zooming in, we see that the last crossing is between 5.5 and 6. So then find it exactly with fsolve. For this part, we might go on a completely new line just to copy over this temporary bit of information itself. Okay, so there's our zoomed in plot. And we go, okay, 5.5 to 6, and include the code and the solution. Therefore, the last time the module is more than 5 meters away is at t equals 5.82 seconds. Done. Okay, next part. After analyzing its motion from the photon torpedo hit, a Borg ship determines the module's resonant frequency and targets the module with a pulsing wide-angle particle beam tuned to this frequency. The particle beam behaves like a periodic wind with the wind velocity of 1,000 meters per second times 1 plus sine of omega naught t, and subjects the module to a drag force given by Fd is negative 10 newtons per meter per second squared times vrel times the magnitude of vrel, where vrel is the relative velocity of the module compared to the wind. When the Borg ship turns on the particle beam, the module is initially at x equals 0 with v equals 0. Write the net force on the module. Assume the EM damper from part 1 stays on, the springs stay in their linear stage, and the problem is still one-dimensional as the module moves along the line of the springs. You can refer to the expressions defined above or in part 1. Then we're going to write the system of first-order DEs you would use to solve this in FlexPDE, sketch the solution for t is 0 to 40, or just copy down the plot from FlexPDE, and determine the steady-state equilibrium position while the beam is on and the steady-state amplitude of the motion it causes. All right, so we're evidently going to use FlexPDE for this part of the problem. Even if the question didn't tell us to do this setup of the problem in FlexPDE, we would still want to use FlexPDE for this because of this nonlinear force that we've got. So this is going to make it more difficult for us to solve the situation in Maple. Okay, so if we go back up to what we have so far, we can make an adjustment to what the new net force would be. But you know what? Before we do that, let's just go back up and double check what the resonant frequency is. So from the plot, it looks like the period should be about 3 and a bit seconds. That's how long it takes for this to be repeating itself. And we can figure out what omega naught is and then convert that to the period to check whether that agrees here, and then use that to make some predictions for what we think is going to be going on in the FlexPDE version of the problem. Okay, so back up to this, we'll say that omega naught is equal to square root of 2 times k over m, and we can evaluate that to calculate what it is. Oh, so omega naught is exactly 2, which is not really surprising because 2k is 4,000 divided by m is 1,000, so we have root 4, so that's 2. Okay, great. So to figure out whether or not we should get a period of a little bit like 3 for that, let's think about how omega naught works in harmonic functions. We'd have sine of omega naught times t, and the period of sine is 2 pi, so this would repeat omega naught t. If you wanted to kind of see how often this would repeat, think about the whole thing's going to repeat whenever time goes through enough to make this whole thing equal to 2 pi of a shift. So what you need is that omega naught t must be equal to 2 pi, and therefore omega naught is equal to, or rather t is equal to 2 pi over omega naught, and vice versa. So if you take 2 pi and you divide it by 2, then we should have a period of exactly pi, which is kind of what we saw from the plot, right? It's a little bit more than 3 is what we saw for the period of this. Okay, so moving on, we've got our original net force, but we're going to add to this the net force from this this wind force here. So let's see, we can go and kind of take the information that we need from that. So we're going to say that we're going to subtract 10 times, actually let's just say minus FD, where FD is equal to this, and then we'll say vrel is equal to that. Okay, so there we go. That's pretty much it. But write the net force on the module. Did they tell us to sub in everything? Nope. You can refer to the expressions defined in part 1. Okay. So we've got 2k and negative b, and there we go. There's the net force on the module. So write the system of first order DEs you would use in FlexPDE to solve this problem, and you can refer to FNet from part A. Wow, okay. So that would mean that we've got a position differential equation, which would be, you know, let's actually not use math type for this so that we can just kind of write it as it would look in FlexPDE. So we're going to have a position variable, and the time derivative of xd is equal to negative v. Wait, what am I talking about? Negative is equal to vx, right? The x velocity is the time derivative of the x position, and then the derivative of velocity is equal to the acceleration, which we could just jump to writing as f net divided by the mass. Okay, so there you go. That's like written directly in the FlexPDE notation. If we did want to write it in the regular math notation after all, then we would say the time derivative of position is equal to the velocity, and the time derivative of velocity is equal to the acceleration, which is f net over the mass. Cool. So there's the system of differential equations. To show that it kind of goes together, you can put it in like a curly bracket like that. So there's the system of first order differential equations. Sketch the solution for t equals 0 to 40, identifying the transient and steady state parts of the motion. Right, so now is where we'd actually need to go ahead and solve this. Let's get our FlexPDE code here. We've got a new problem that I've just saved as a 2016 T03 video redo name. So let's call this T3 prep. And what do we need? We're going to have XD, threshold is 0.1, and we're going to go with Vx for the second variable, and grid is 1, and set up some definitions. Now first, actually, a good idea is to solve the problem from part A to test that the code is working before we go and adjust it to do other things. So let's say M is 1,000, B is, or rather, K is equal to 2,000, and what was B? B is equal to 500, I think. Let's jump up and check that. Yeah. So the initial value was a position of 0 and a velocity of 50. The differential equation is going to be that xd is dt of that is vx, and vx dt of that is equal to fnet over m. Fnet is equal to negative 2 times k times xd minus b times vx, and we're going to need the time range 0 to, let's just plot to 10, what we did in the first part, and then we'll need for t equals 0 by 0.1 to n time history xd at 0, 0. That should do it. I don't think I made any mistakes, but let's just see how that works. Okay, so there is the plot that we had. I wonder if we can add in, I'm not sure we can do history plots of just constants that we just defined down here. Let's see, can we do 5? Oh, right, yeah, it looks like we can, but it goes on a new plot the way I did that. So here's kind of what we wanted, xd 5. Yeah, there's our vertical line, or horizontal line above there, and we'll put in negative 5 too. Cool. very very well produced, very good at reproducing the results we had from the first part. Nice. So the next thing to do is to add in this much more complicated force for the to deal with the wind that's being applied. So let's define the wind, let's define the relative velocity, and then let's add in this new damping force in those three steps. So first, the wind is equal to, we'll actually need to put this above Fnet so we can add it in to Fnet later. V wind is equal to 1,000 times 1 plus sine of, what was it, W naught T? Yeah. W naught times T. We will define W naught is equal to the square root of 2 times K over M. Only 2K because we have two springs in this. So the default, remember, is the natural undamped resonant frequency is root K over M. The reason we're using that is because it's basically the same as the damped one for this kind of damping where we're underdamped. Okay, Fnet is going to now account for this wind velocity force through Fd, F damping, which is -10 times Vrel. So we'll need to define that. Vrel is equal to Vx minus V wind. And then we've got -10 times Vrel times absolute value of Vrel. And we'll say that, oh, you know, does this make sense? We said that I guess there's a problem in this test. We said that the damping force is, we're sort of adding negative Fd, and we've gone and put this as a negative thing in terms of Vrel. So I think that was a correction during the test. We need to, oh, wait a minute. No, sorry. That's a mistake that we just made. We subtracted Fd rather than adding it in. Yeah, okay, much better. So we're adding Fd. We're going to say Fd is this thing, and so hopefully you noticed that earlier, and we're just screaming at the YouTube recording here, YouTube video, and caught that. But if not, then maybe watch these more critically. Again, not perfect. So Fnet is this plus Fd, and Fd is negative. We've made sure that it moves in the right direction. So actually, maybe it's worth thinking about how we predict that this is going to make the thing move. Generally, the wind is in the positive direction. In fact, so because of the 1 plus sine omega t, it is entirely in the positive direction. And the average value of the wind is going to be when we're at an equilibrium. Sort of, if you look at the plot of this, it's going to average around 1,000 meters per second. And then the drag force is -10 times the velocity of the wind squared. So we got 10 times 1,000 squared at that average spot. So that's going to be 10,000 squared is a million, 10 million newtons. The springs at that same spot are, so to counterbalance that, for the springs to be resisting the sort of steady state wind force, they would have to be producing 10 million newtons the other way. And since the two springs together produce 4,000 newtons per meter, you would need a, let's think, you'd need a displacement of, if you had a displacement of 1,000, you would get 4 million newtons per meter. But we need 10 million newtons. Sorry, if you had a displacement of 1,000 meters, you'd have a force of 4 million newtons. And to get that 10 million newtons, you'd then need not 1,000, but 1,000 times 2.5, because 4 times 2.5 is 10. So around 2,500 meters of displacement. In fact, we probably would expect a little bit more than 2,500 meters of displacement, because the force is based on velocity squared. And when you've got this thing moving between 0 and 2, then the square is going to make a bigger difference at 2 than it makes on the other part. So it goes up to 4, it goes down to 0. Even though the average is 10 million, this is going to be a plot that goes between 0 and 40 million. So that's the prediction, is that the springs, since they would balance at 2,500 meters of displacement, we probably have a steady state displacement that's a bit more than 2,500 meters. So if we go to FlexPDE now and make this thing run, we've got a displacement which so far has reached around 2,200. That's not as big as it should be, but I don't think this is actually stabilized. So let's take the time further. And the question told us to plot to 40 seconds. So let's just do that. Okay. Oh, actually it's pretty much exactly 2,500 meters for the equilibrium position. So perhaps that square part doesn't make as much of a the velocity going up to 4 doesn't actually make that much of a difference when it comes to squaring that at the other end compared to the 0 at the spot before it. So maybe the square balances out front and back. Anyway, the question asks us to figure out the steady state amplitude, which is 2,500 meters. And wait, sorry, the steady state, the equilibrium position is 2,500 meters, and the steady state amplitude on that is how far we're moving from that equilibrium. So the offset, I guess I should say, is 2,500, and the amplitude is 500 meters. Yeah, determine steady state equilibrium position, so that's 2,500, and the amplitude of motion that it caused is 500. See, we've moved to this new position up there, and we've got that amplitude around it. So let's think. How could you adjust some of these things and see how it would affect the result? If the frequency was different for the wind, then because we are not at the resonant frequency anymore of this system, you'd expect the amplitude might get lower, but the equilibrium offset position shouldn't change that much. So if we go back to the problem here, and now imagine that instead of omega naught, we're going to use 4 times omega naught. So the wind is not any stronger, it's just oscillating faster. So this should probably give the same equilibrium position, but a smaller amplitude. Let's check. Yeah, more or less. This actually maybe emphasizes that the equilibrium position, so it actually got to a bit larger of an equilibrium position than before. I wonder if that was because the averaging happens in the right way now, or just we had more time to stabilize because of the steady state being faster. We can do the opposite. We can go 0.25 times omega naught and see how that behaves. So this, interestingly, gives a much bigger amplitude once it's looking like it's stabilizing. Very interesting. So we said the omega naught is root of 2 times k over m. And just changing this to a much smaller frequency seems to have increased the motion of this by quite a lot. So that's not normally what you would expect for a force that's applied, and that's because the force has to do with the relative velocity here. So if instead of that we were to just plot, we were going to make the force the wind directly, maybe times 1,000 to make it about the same size. Now we've got a response like this at low frequency. If we move up to the resonance frequency, we get a larger amplitude, and if we move above the resonant frequency, you have a smaller amplitude. This behaves more like we would have expected from the regular behavior of the force when we're driving it. But this weird particle beam is actually kind of applying a damping that opposes motion relative to its steady state wind velocity. So in some ways it behaves like a regular resonant system, and in other ways it behaves very strangely, where you get more of an amplitude at low frequencies than you do at higher frequencies. That kind of makes sense in a way, because damping opposes additional changes in, it kind of opposes velocity. So trying to make this thing move faster back and forward tends to be like a secondary effect that limits the amplitude of this.